Hey everyone, welcome back to my Calculus 2 series. In today's lesson we're going to be talking about trigonometric substitution. So in today's lesson we're not really going to be talking about trigonometric integrals, like they won't be containing things like sines or cosines or tans, but they will be dealing with integrals that have stuff in the form of this. Like we'll have the square root, and then maybe we'll have something like a squared minus b squared. So we'll be dealing with like integrals in this sort of form, and you'll see why it's called trigonometric substitution. It's because we're going to use kind of the properties of these trigonometric functions to sort of simplify these types of forms, but it doesn't really have to do anything with sines or cosines or any other trigonomic functions. So the lesson itself is pretty short. Essentially, we're going to solve for integrals in three kinds of forms. So the first form is the a squared minus x squared. And if we are given an integral that contains this sort of thing inside of it, where obviously a is a constant and x is the variable, well, then we're going to use this kind of simplification method. So that we're going to say 1 minus sine squared x is equal to cos squared x. And again, you'll see later on why we do this sort of substitution, but essentially you can see why, right? If we have this thing right here under the radical, and then we simplify it, and we're just going to have cos squared x, well, if this term itself is going to be cos squared x, we can easily take the square root of that and just be left with cos x. And that's what this whole kind of lesson is going to be about. It's going to be simplifying these square roots. Now the next form that we can have is the square root of a squared plus x squared. And what we want to use if we have an integral containing this is the 1 plus tan squared x equals to secant squared x kind of identity. And lastly, if we have an integral that contains the square root of x squared minus a squared, well, in that case we want to use kind of the opposite of the second one right here. We're just going to say that it's secant squared x minus 1 is equal to tan squared x. And again, let's not confuse. X is an actual variable that we're going to be having, and a is some sort of constant. So I feel like the best way to learn this type of content is through examples. However, they're all, like, we're going to go only through, as we can tell, it's this one, number 1, but the steps will remain the same. Again, you're just using a different identity to kind of simplify it. So if you know how to do it with one, chances are you probably know how to do the other formats too. So let's say we're given this integral here, and we're asked to find, okay, what is this equal to? Well, again, I've sort of mentioned it, but this looks like this form right here. That's because we have a constant squared. So in this case, it's going to be 3 squared because it's a 9, and then we have minus x squared. So we're going to use this identity right here to sort of simplify things. Now, here is the way we would go about simplifying it. So firstly, as we can tell, in order to use this identity, we need a 1 here, right? We need 1 minus sine squared. So we need to get this 9 right here to a 1. How can we do that? Well, we can factor out a 3. It would actually be technically factoring out a 9, but because we're bringing it outside of a square root, we need to take the square root of that number, so it's going to be 3. So if I bring out a 3, this is going to be a 1 minus, and then we're going to have x squared over 9. Again, if you don't see what I did there, essentially, I kind of, if we have this square root, I did 9. I factored out a 9 from here, so 1 minus x squared over 9. And then I brought this 9 out, so it was going to be 3 times the square root of 1 minus x squared over 9. That's what I did in this step right here. And now, again, over here we can notice that we have a singular term. We don't really have two terms like we have here. We have x squared over 9. So an easy way to combine them would just be to bring that 9 under the square 2, and you'll see what I mean. So there you go. I've brought the 9 kind of within that square by simply taking the square root of it and putting it onto kind of the same term basically as x. So now we have x squared over 3 squared, which is essentially the same thing as this right here. And now we finally got to the point where we have something that looks like this format, and we can finally start applying our substitution. So we could see that we need to sub in for the second term, we need to sub in a sine, right? We already have the squared, it's right here. So we need to have the sign in there. And the way we can do that is, well, the term we have currently is x over 3, but we need that to be 1 minus sine squared. So we're just going to say that, okay, well, this is going to equal to the sine of theta. And now if we simply plug that in, we're going to have something like this. So there we go. We have plugged it in and we've got where we want it to, except now we kind of need to we have two variables in here. We have thetas and we have x's, and we want to sort of convert everything to thetas because now that's what we've made our substitution with. So we can do that in a couple of ways. Firstly, we need to get rid of this x squared and the dx. So let's get rid of this x squared. And how would we do that? Well, we know that x over 3 is equal to sine theta, but what is x squared going to equal to? Well, we can just rearrange this real quick and say that, okay, well, x is equal to 3 times sine theta, and then x squared, well, it will equal to this squared. So x squared equals to 9 sine squared theta. There you go. And now that's another substitution that we should be making. So now all we need to do is cancel out dx. And the way we can do that is, again, if we were back at this step right here, we can just take the derivative of here, and it's going to be dx over d theta. The reason it's going to be over d theta is because this bottom value tells us with respect to what variable, and as we can tell, our function has the variable theta here, so that's why it's going to be d theta. Now dx over d theta, well, that's going to equal to 3 times cosine of theta, and then dx is going to equal to 3 times the cosine of theta d theta. So now we can make our last substitution in here. And there you go. We have finally gotten rid of all the x variables and everything looks good. Now the next thing to do is to notice that we have substituted this 1 minus sine squared theta in for a reason. And if we go back, it was because we wanted to use this formula right here. We wanted to simplify it to be cos squared theta. So let's go ahead and do that. So there we go, and now an easy simplification that we can see is because we have reduced it down to one term, we can now take the square root of that term. So now, as you can probably tell, there are a bunch of simplifications that we can make, and I'm going to go ahead and do them. So there we go, we have simplified this integral and we've ended up with the integral of cotangent squared theta. And we can kind of simplify this integral by using this property that the cotangent of squared theta is equal to the cosecant minus 1. So now if we make this substitution in for here, we're going to get that this is equal to the integral of cosecant squared theta minus 1 d theta. Now again, we can distribute this integral. And now we can take the integrals of both of these. So we're going to get that, that this is equal to the minus cotangent theta minus theta itself, right? Obviously plus c. But now we've gotten rid of the integral sign, but we're not quite done yet, right? The question started off with asking us about the integral in terms of dx, and all of a sudden we've ended up with that same integral but in terms of theta. So now we kind of need to convert back from theta to x. So how can we do that? Well, let's take a look at the initial substitution that we made, right? It was that x over 3 is equal to sine theta. One way of putting this, if you remember about anything about angles and geometry, well, if this was the angle, then what this is saying right here, what this this expression here is saying, well, sine, we know that it's the opposite over the hypotenuse, right? So the opposite would be here and then over the hypotenuse, which is a 3. So we're going to label the opposite side of this angle the numerator, and then the hypotenuse is going to be 3. And now we kind of have this right angle triangle, and we can use Pythagorean theorem to figure out what this other side would be, right? Well, the other side would be if we have c squared is equal to a squared plus b squared, right? Then a leg in this case, so a would be like a squared is equal to c squared minus b squared. And we can use this formula to figure out the other side. So actually it would simplify to the square root of c squared minus b squared. So in this case, it would be the square root of 3 squared minus x squared. That is the value of the other side. Now if we think about it, what is cotangent? Well, cotangent theta is equal to 1 over the tangent of theta, right? And we know that the tangent of theta is the opposite side over the adjacent. So just tangent theta would be x over the square root of 3 squared minus x squared, because it is the opposite side over the adjacent side of that angle. However, that's not what we're looking for. We're looking for 1 over the tangent. So essentially all we need to do is just flip this fraction, and we're going to get that it's equal to 3 squared minus x squared over x, right? And that's our cotangent. So we're going to get minus the square root of 3 squared minus x squared over x, and then minus theta plus c. However, what is theta? Well, we can use just this formula right here to solve for theta. It's nothing complicated. All we need to do is just take the inverse sign. So this is going to be sine minus 1 of x over 3, and then this is going to equal to theta. So we make our last kind of substitution, and we are done. So there we go. We have finished this integral. And you can see the steps. All we do is we do that substitution. Then we kind of try and get rid of these up here. We were trying to get rid of these like dx's and x squareds by just manipulating the substitution itself. And after that, we do a bunch of simplifications. And finally, we solve that integral in terms of what we substituted in for. We get an answer in terms of what we substituted in. And then we kind of try and work our way back by using this triangle method right here and this inverse method right here. Now that stays like for all the trigonometric substitution integrals that I've done, the procedure stays the same. So you can kind of apply this to any of these 3 cases and you're pretty much set. Like you just need a little bit of practice with them and you're pretty much good to go for like an exam or something. So yeah, that's it for trigonometric substitution. It's been a pretty quick lesson. Hopefully you guys have enjoyed this video. Hopefully it's helped you out with something. If it's helped you out at all, please like and comment as to what I helped you out with. Like usual, if you're new to the channel, please like, comment, and subscribe. And yeah, I will catch you guys in another video.